We are going to look at finding the fifth root of a monomial, and we are going to do this as an exercise without a calculator and looking at strategies for how to do that. So the first thing that I'm going to look at is I'm going to look at just the number 32 and ignore the variables here. And I'm going to pull 32 off to the side. And I want to use a technique that you have probably seen in middle school. I want to make a factor tree for the number 32. Since the number 32 is even, I know that at minimum a 2 will divide into that. So I want to do that. 2 is a prime number, so this is part of the prime factorization for this. 2 divides into 3 one time, leaving a remainder of 1. We have 2 divides into 12 6 times, so I have 2 factors here. I have a 2 and a 16. 2 is prime, so we're done with that. That's one of the roots, or one of the prime factors. And we are going to continue. So we should know that 8 and 2 give us 16. Again, we have a prime number here. 8's composite, so we continue on. 4 times 2, and then 4 can be divided out into 2 and 2. So I have these are my prime factors. So I have 1, 2, 3, 4, 5. So I have 2 to the 5th power as my prime factorization of the number 32. So that means that 32 is equal to 2 to the 5th power. This concept is important. I'm going to substitute 2 to the 5th power into here instead of 32. So I'm going to rewrite this. Alright, so this is equal to this. I've taken the 32 out and substituted in 2 to the 5th power. Now I want to look at one of my variables. I'm going to look at n to the 13th power. I've pulled that off to the side here. I want to rewrite this so that it also has a 5th power. Why is my target 5? Well, the index on this root is 5, so that's why 5 is important to me. I want to rewrite this in a way that I have something to the 5th power, and this is going to take some exponent rules to do this. What can I do to make something have a 5th power for this? So one of the things that I want to do is I want to look at a couple of terms that I can multiply together to give me a sum of this. So some number and some number. Another way to think about this is what number, say a plus b, is going to be equal to 13. And then this is going to be my a and my b. If you remember exponent rules, if you have the same base multiplied by the same base but different exponents, then you can simply add those original exponents to get the new exponent here. So I want to have something of this form where one of these is a 5 if I can't have more than one of them as a 5. So I want a plus b equals 13, so I'm looking at the idea that one of these a or b's is going to be 5. So for simplicity, we're just assuming that the first one, the a, is the 5. So 5 plus what equals 13? That should be hopefully a fairly easy subtraction problem for you. 13 minus 5 is 8. And so I can rewrite n to the 13th power as n to the 5 times n to the 8th. So I want to substitute this n for my n to the 13. And then in the same way, I have this j to the 7th power. I want to do the same thing. I want a j to the 5th power times some other number. 7 minus 5 is 2. So I'm going to substitute this expression in for this term. All right, so I substituted in j to the 7th for j to the 5th times j to the 2nd, and substituted in for n to the 13th as n to the 5th and n to the 8th. So now what I'm going to do is I'm going to kind of push all my things that have something to the 5th power to one side, and the reason I can do that is because this is all multiplication of terms under this root sign, and so I have the commutative property of multiplication allows me to reorder these. So I have 2 to the 5th, j to the 5th beside each other. I want to bring this n to the 5th over here and kind of have this group of terms together. And then I'm going to put those in parentheses, and I can do that by the associative property. All right, so I have all these grouped in parentheses now, and these two terms are being multiplied by this, but they're on the outside of the parentheses. So the associative property allows me to group things together, and I can claim that I'm multiplying these first before I multiply these things. The next thing I'm going to do is I'm going to use another exponent rule to pull this 5 outside the parenthesis. So I have that my previous step is going to be equal to this step. I have 2 times j times n to the 5th power, and that's on the parentheses, and then that's going to be multiplied by j to the 2nd and n to the 8th power. The reason I want this form here is because this and this are inverse operations, which means that basically this root symbol is going to eject 2jn outside. So 2jn is coming outside, and the j to the 2, n to the 8 is going to be stuck inside. Now I said earlier, when we looked at the n, that I wanted these terms to be n to the 5th and some other number here, and then j to the 5th, some other number to here, if we could only get 5 out of this. If you look at this, what I have left inside here is j to the 2nd, and there's not a term of 5 that I could subtract out of there without getting a negative number, but 8 can have 5 subtracted from it, and I wouldn't get a negative number. So I'm not quite done with this process, but we've seen the general idea of what we're doing. We're trying to regroup things so we have something to the 5th power, so that this 5th root here is going to act as an inverse operation here. So one final thing is I'm going to relook at n to the 8th power, and I'm going to do the same thing that I did up here. I want n to the 5th power times n to some other power, and those powers have to add up to 8. So we're going to have a 5 and a 3 here. So when I plug this term into here as my substitution, I'm going to have the terms still on the outside. My j to the 2nd is going to be in there, but I'm also now going to have n to the 5th, n to the 3rd that I substitute in for my n to the 8th. And now this 5 and this n are inverse operations, so it's going to kick this n out. And I'm going to do this in steps so that we can see what's happening. I have 2jn times n that I just kicked out because of the inverse operation here, times the 5th root of j to the 2nd power n to the 3rd power, and now there's no 5 that I can subtract out of this exponent, so these are basically what I'm going to have left on the inside. There's nothing more that I can do to simplify this. There is something on the outside, though, that I can do to simplify this. I'm going to take this n times n and rewrite this with an exponent. So I'm going to have 2jn squared times the 5th root of j squared n cubed. And this is my final answer. This is a simplification of the problem that we started with up here. So we've done all this simplification just doing some side calculations by hand using our middle school technique of factor tree, and then doing some applications of the exponent properties here. So this is equal to what we started with.